Okay, thank you very much, everybody, for attending this talk. Again, I've had a blast. This is, again, day 2 of Fluttercon USA 2024. So I've had a blast. Has been an amazing conference. There's been great plethora of amazing sessions. I hope you guys have been enjoying it. And again, thank you for picking my session as well. So my name is Roman. I am a Flutter GDE. I am also a lead organizer at GDG Lawrence. I definitely love to share my passion about Flutter with the whole community. I work at Philips Healthcare. I am one of the lead developers there. I work at the ultrasound division for Philips. And this presentation is actually going to be delving into Dart FFI. For those of you who may, are exploring or are even tapping into low-level capabilities, of your applications, talking to low-level languages like C, C++, Go, Rust. We're going to be talking about that, but this is mostly particularly in healthcare. We'll explore how Dart FFI bridges the gap between Dart and C++, enabling developers to leverage the power of existing C++ libraries. Let's say you already have a C++ library that you want to tap into from your Flutter application. Also, not only to perform, let's say, complex data analysis, machine learning, or just leveraging existing C++ libraries, and of course, deliver exceptional performance on CPU-intensive tasks. Especially me, because I come from the healthcare industry. The healthcare landscape is undergoing a digital revolution. And Flutter is emerging as like one of the top players out there as a powerful tool for crafting innovative medical applications. The history of Flutter at Philips Research in Cambridge, Massachusetts, this is where I come from. It started 2 years ago, and again, this is a very quick story that I'm going to share with you. One guy came up to our team and he said, "I've heard of this amazing framework that will revolutionize the way that we build applications within Philips. One single code base, natively compiled applications, beautiful, high-performant UIs." The guy came up to our manager. He gave a demo. He gave a presentation. Our manager said, "Say no more. I'm completely sold. Let's go with Flutter." Everybody thought it was like too good to be true. It was like that's like really too good to be true. The guy went off. He built a quick prototype. Like in 2 weeks, he came back. It was amazing. Then after that, he onboarded a couple more people to this framework. Fast forward to today, the project is funded by the Bill and Melinda Gates Foundation with a $15 million grant, and we are well on track for delivery. It turned out that that guy was me. So I'm really proud of having introduced the team at Philips Healthcare to Flutter. They were like naysayers at the beginning, but they're like, "No, I think we're all behind it." They love it. I've onboarded an amazing team, and we've been reaping the benefits of Flutter within the healthcare, specifically in Philips, and of course, making us more productive while providing the best patient care through it. So again, like I mentioned, the healthcare industry is undergoing a profound digital transformation fueled by advancements in technology and the increasing demand for accessible, personalized care. Flutter is uniquely positioned to drive this innovation in this era of healthcare with its ability to create beautiful, high-performance applications across multiple platforms. The device that you see right there, I actually have it right here in front of me. This is the Lumify. Actually, let me just go back one more time. Here it is. This is the Lumify C5-2 transducer. This is a curved array transducer. It has a 50 millimeter radius of curvature. This is very heavily used in OBGYN, in lung imaging preset optimizations. It has a 5 to 2 megahertz operating frequency range. And this is actually the device that we interact at Philips. There are many other range of high-end devices that are actually helping us and helping healthcare physicians out there to actually be more productive. So why Flutter? So why do we pick Flutter? So Flutter, again, I know that I'm preaching to the choir, but of course, Flutter gave us so many benefits. Of course, one single code base. In order for us to target multiple platforms, saving development time and resources. So as you see, we have a very small team, but we've been able to deliver great, we've been able to make great strides with that. Flutter, of course, enables us in the medical industry faster development cycles, meaning we can actually get to market much quicker and more focus on quality and user experience, right? Also, the fact that Flutter compiles to native code ensures high performance in medical applications, because as you know, smooth user experiences, every second counts in the medical industry. So it is very important, it's very crucial in the medical industry. Also, the fact that the customizable widgets provide control over the app's look and feel. It is very paramount at Philips in order for us to create that harmonized user experience. Wherever you go to a hospital and you see one of our devices and you interact with our UIs, you would immediately identify it. And that is exactly why Flutter has given us that flexibility. Also, the fact that Dart's bridge to native APIs, it gives us access to platform-specific features. Like cameras, sensors. We have a bunch of sensors, like patches, like some of these handheld devices for performing like ultrasound exams. It is essential for Philips' focus on innovative medical technologies. And last but not least, of course, Dart FFI, which enables seamless communication with external libraries written in other languages, not specifically in Dart, but it gives us those capabilities and a lot of integration possibilities. So then why C++? Because we could have picked maybe any other low-level language. But the fact is that at Philips, Dart FFI plays a crucial role in leveraging our existing C and C++ libraries. And a huge code base, a lot of expertise, a lot of the research within Philips has been captured in some of these models. It allows us to reuse legacy code, and even we can just wrap it around, some other code and actually ship it with our applications. We can access platform-specific features and optimize performance-critical tasks. Additionally, FFI enhances Dart's interoperability with other languages. Like I mentioned, like we've even been able to interact with Go, Rust, Python. And of course, that kind of expands Dart's interoperability range of how many languages we can interact with. And it gives us a wide range of possibilities and even bring in more developers into our ecosystem. So I'm going to just play a quick demo on the application that we're actually building. This is the application that we've been building for the past year with successful pilots in both Kenya and India. It's called iMama, which stands for Intelligent Mobile Access to Maternal Assessment. This project is an AI-based application. It's made to improve the quality and accessibility of OBGYN care in low and middle income communities, mostly underrepresented communities in these, like really remote villages, by helping frontline healthcare workers such as midwives, nurses, to identify potential problems, during the pregnancy at an early stage. The project aims to significantly reduce the number of women who die every year as a result of, a pregnancy. Currently, around 830 women every day worldwide, while reducing fetal mortality and morbidity. This application, again, like I said, is fully developed in Flutter. We're tapping into some of those low-level capabilities that we've built in C, C++. Also, some of the animations are also built in Rive. I don't know if you guys have heard of that library as well. And you see it's very smooth, it's very seamlessly integrated into our applications, and we're able to even package it as a module, as a Flutter module, and we can even do it as an add-to-app to other applications within Philips. So the current landscape, as far as like Dart interoperability, again, this is pretty much the current landscape. The FFI Gen package, some of you may have heard, in Dart is used to generate bindings to C. Also for any other languages that compile to C or are kind of like compatible with it, like Go, Rust, some of those APIs, allows us to interact with the, let's say you could use FFI Gen, and then it generates the bindings for those. One thing to note is that FFI Gen only supports parsing C headers, not C++ headers. Also, it supports Objective-C and Swift APIs by generating Objective-C headers using the FFI Gen. So you can use FFI Gen for both C headers, Objective-C headers, and Swift APIs as well. And last but not least, then you have the JNI Gen, which you may have heard in a few talks here during this conference. So for Java and Kotlin APIs, for you, let's say if you want to tap into, let's say you have jar files, you have some of that knowledge already compiled into jar files, you can generate, automating the generation of Dart bindings for Java APIs. And let's say if you have more newer packages and libraries that you want to tap into, Kotlin can also be used with JNIGen by compiling it to Java bytecode. So you can compile to Java bytecode, and you can use JNIGen to tap into Kotlin. So let's start. So Dart doesn't necessarily call C++ code. Instead, it uses FFI that actually bridges the gap between the two languages, as you can see right there. But this is how it works. Now let's dive right in. So to interact with Dart, the C++ code needs to expose functions with a C-compatible interface. This often means declaring functions. Maybe some of you have done it. You have to do extern C, and then you define all your functions in there to prevent name mangling. And the reason is that Dart FFI and the FFI gen package, like I mentioned, only supports C headers as opposed to C++ headers. And then the C++ code is compiled into a shared library. Some of you may have heard like an SO file, a DLL, a dilib file. All that code is compiled into a shared library, and then it can be dynamically loaded or statically loaded. The process of building that library, those shared libraries, can kind of slightly differ between platforms. Let's say if you want to build this application, but you also want to tap it. Let's say you want to build it for iOS, you want to build it for Android, for Windows, for the web. You can then, of course, some of these nuances are differ. But the process of building those shared libraries is slightly different between those platforms. But FFI, great thing, the FFI provides those tools to handle these platform-specific nuances. Now, stepping one step much deeper. So the Dart FFI, starting from the top, if you see, it provides functions to load the shared library by, let's say, if you want to load it statically or dynamically at runtime, you could use dynamic library.open. You provide the path to your library, and then you can load it at runtime. Those shared libraries, like I mentioned, SO files for Android and Linux, DLL for Windows, dilib for Mac OS and OS, then that kind of like encompasses all your code. But it contains not only the C++ code that is part of your library, but you also have to bring in some other components in there. Once it is loaded, let's say your dynamic library is loaded, Dart FFI then looks up the addresses of those specific functions in your C library that you want to call. Dart FFI then provides some specific types, and let me see if this works right here. So for example, Dart FFI provides some types that actually map to types in C++. That's how the bindings get created. For example, here, if you see, this is void for the Dart aspect of things. This is the FFI type that maps to a void, let's say, in C++. For example, here, a pointer of uint8 image, for example, this is pretty much an unsigned list of 8-bit integers, right? In C++ is an uint8 list, which you can represent pretty much as a byte array. Same thing with an integer. You have an integer on Dart. You have int32, and then it maps to an int32 pointer, or like the actual representation of an integer in C and C++. Then then this is the bindings that that creates. Then when the Dart function calls a C function, just Dart FFI handles the marshalling and unmarshalling of the data. If this data, let's say you want to pass some data to C++, it gets converted. Dart FFI takes care of marshalling and unmarshalling the information before and after the call. And then just Dart executes the C function directly. So now we're stepping back one more time. So your custom native code doesn't know about Dart. For example, like our libraries within Philips, they don't know about Dart. It doesn't know about FFI. That's the reason why you have to create some sort of a thin wrapper between, let's say, your custom libraries, your third-party libraries, your, let's say, TensorFlow libraries, and let's say, whatever you want to do, like all the marshalling and unmarshalling and the whole like Dart FFI connectivity, right? But you have to package it up with some elements of the Dart runtime, which I'll explain in a minute, so that you can actually establish that communication back and forth within Dart. But you have to do the same thing on the Dart side of things. You have to define kind of like the bridge that marshals the information to be consumed by C. You can also, let's say, you can create some listeners so that you can, let's say, receive the communication and any notifications from your low-level libraries, and you can capture it on the Dart side. You can, create, like I said, like listeners, receive notifications. You could do like pub sub, whatever you want to do. But you have to do this yourself as part of your application's architecture, of course. So in the application that we're building now, this is a much higher level architecture of the application. So you see how, for example, in this case, images are being streamed into the Flutter application, either from, let's say, a local SD card, from the local device, or maybe they could be streamed from the actual ultrasound machine, whether it's like gRPC, whether it's sockets, what have you. This communication is handled in the background by a separate isolate, ensuring that the main isolate remains uninterrupted, doing what it does best, which is painting pixels on the screen. The UI thread then just focuses on rendering the visuals, while the background thread, for example, here we instantiate kind of like an isolate that handles all the data, all the incoming data. It handles all the incoming streams. And as we all know, it's just a small review, Dart code execution is single-threaded, as everybody knows, but it uses isolates kind of like to achieve concurrency, right? In this case, we're trying to keep the UI thread pristine, no drops of frames, no UI jank or anything like that. All the heavy lifting happens either in the low-level aspects of the application, sometimes then within an isolate, and then we just keep everything separate, and those like heavy computations are deferred to other isolates as opposed to the UI thread. But again, as everybody knows, isolates have an independent memory space. Communication between isolates actually happens between these concepts called receive ports and send ports pairs. We're going to be discussing that in a minute. So the three approaches, because everybody knows that Dart FFI doesn't support asynchronous functions, right now, Dart FFI are synchronous in nature. All the calls to the Dart FFI are synchronous in nature. So the three approaches that we're going to be discussing today are native ports, which we just showed a little bit. We're going to be talking about asynchronous callbacks or async callbacks, and the native callable, which actually was added to the Dart language in 3.1. And this is something that you guys should be paying attention to if you truly want to leverage Dart FFI while tackling non-blocking asynchronous messaging between Flutter and your native and your native code, let's say C, C++, and whatnot. So let's start with native ports. So I just explained it. So let's start from the beginning. So in order to establish an asynchronous communication with your native code, you need to instantiate a receive port. So the receive port is a fundamental component used for asynchronous communication, particularly among isolates, like I just mentioned. But receive ports are known as the only means of communications between isolates. Each receive port then has something called a send port. The send port is what you use to send messages to this corresponding receive port. It's a port, but not in the concept of like networking. It's mostly like a pointer. It's kind of like a remote procedure call almost. So the send port, instead of using the actual send port to send information to receive port, you actually use the native port of the send port. But the way that happens, the way that what I'm showing right now here is that the receive port has something, provides like a stream so that you can listen to incoming messages for anybody that wants to send information to the receive port. And then using the native port of the send port, you send it to C++, or you send it to the C, let's say to your low-level library, in this case C, and then using that native port, you can send messages back to Dart using this concept of a Dart post C object. So let's say you can send any type of payload. You can send, you can send an image. You can send a JSON. You can send, any model. You need to use the port, pass the payload, and you can send it over to the corresponding receive port on the Dart side of things. And then this is what they call the post C object. And then the C++ code interacting with this code, the C++ code that actually interacts with the Dart native API, you actually have to bring it into your library because it's, your code doesn't know how to talk to Dart. And this is exactly what I'm going to show in just a minute. So here it is. So initially we do like a proper initialization. We do the proper hooks. We do again, all the heavy computations happen on C++, while the Flutter UI thread remains, again, just rendering the visuals. And this is, at the beginning, we initialize all the libraries, we establish all the communication channels, we do all the hooks, we set up all the listeners, to react to specific events. And this architecture truly and efficiently, again, ensures resource utilization and a smooth user experience in the interface. Now, this is what I was mentioning. So now when you want to exchange messages, what we do is, again, we pass the native port to C++, and then we just constantly listen for C++ to send us information via this native port. And I'm going to show that example right now. So the most of the use cases in for native ports is, again, performance optimization, like I mentioned, for compute-intensive tasks like image processing, cryptographic operations, large-scale data processing, or other significant operations that you want to do. Also, platform-specific APIs. Accessing APIs that are not exposed through the Dart SDKs. Let's say you have a library that, let's say your company already has some legacy code that you don't want to redo, but you want to leverage. You can use native ports for this case. And of course, reusing existing code bases, like I mentioned, leveraging existing C and C++ libraries within Dart or in Flutter, avoiding the need to rewrite all that complex logic. So the first thing that you do, now if you want to get into the nitty-gritty of things, you want to build it. So the first thing that you do is you identify which are the files and libraries that you want to make part of your shared library. And if you see here, I'm going to name my shared library, I'm going to call it Inference Engine, for example. Here, pay attention to this line right here. Then here I just add like OpenCV. Some of you know, for example, like a C++ library called OpenCV for image processing and stuff. You add some dependencies, some other engines and packages. Then this is the key part right here. So in your shared library with your code, you grab the files that are part of the Dart language SDK. This is actually even recommended by Slava. He was actually walking around yesterday here. This is the way that it's actually done. So the way that you do it is you grab the include files from the Dart SDK and you package it up with your own library. And these are the two ones that you're going to pay attention mostly. Dart API DL and Dart API DL header. So the C file and the header file. You actually grab the whole folder because you might want to tap into other capabilities, but these are the two main ones that you're going to be leveraging from your own code. And I'm going to show you how to do that. So now again, for Android, you want to build your library. This is the CMake lists file. Let's say if you want to tap into, for example, your native code toolchain, whether you're using CMake or NDK build. In your CMake list file, you do, for example, I'm going to call it Inference Engine. I'm going to add my native bridge, which I told you need to create a native bridge, and you add all the files from the Dart SDK. Now after that, for example, in this case, this is in the build.gradle. So you set up your build.gradle. Let's say you're doing it for Android. During the build, the configuration specified in the CMake lists file actually gets captured as a shared library. Remember, I called it Inference Engine. So when I run my build, the build Gradle, when it runs, is going to build a shared library called lib, whatever name you put it, .so. That is how now all your shared code, your third-party libraries, the Dart SDK aspect of it gets built into a shared library. Now let's build the Dart side of things. So let's say you just build your C++ shared library. Now you're ready to access it from the Dart side of things. So the first thing you do is you create the FFI bindings. If you use, again, FFI gen, this is generated for you. But because us, let's say at Philips, we do have some legacy code, some C++ some C++ headers, we still have to do it manually, but at least you do it in a very comprehensive way. So the way that you do it, you start by creating type definitions that map to functions that are available in C++. This function right here is available in the Dart native SDK. You need to have this signature right here so that you can initialize the Dart API. So you create a type def with the definition, the FFI definitions and annotations. So you first create that type definition that maps to that function in Dart. Then you create pairs of the functions that now you're going to call into your native code. Let's say you're going to have one method called setDartPortNative that is a void function that takes an integer, for example. Or you create another, actually, let me go back. So you can create another one that takes like a string, and it just returns void. And you're going to call it like send message, for example. But you need to have the FFI signature and then the Dart signature. The Dart signature is that you can then map it and create the binding, and you can call the method in Dart, which actually activates the code in C++. The next thing that you do is you load the library. So remember the library we just created? The way that you do it, you load it by the FFI capability, this FFI method that allows you to load your library. You say dynamic library.open, and then you provide the name of your library, your shared library, and then it gets loaded into the Dart VM. Remember, you can load it either statically or dynamically, but by doing it like this, you're loading it dynamically. Dynamically, it gets loaded, it gets created as a separate file, and you can just invoke it on demand. Anytime during your program's execution, you can load it, but if you load it statically, it's actually part of your executable, and it loads as your application starts. Then the next thing that you do, you perform lookups. The lookups are like you finding, after you do the bindings, now your module, let's say your shared library, is able to find those functions in C++ using those type definitions, and then you can call those functions directly from Dart. Then you can just say, okay, did the library load successfully? After you know, for example, I think the value just returns 0, and then that means like the library loaded successfully. Then you can do more lookups. Let's say now I'm going to find that method that is called setDartPort. I'm going to send it an integer, or actually I'm going to send it the value of the native port that I wanted so that I can send information back up to Dart. And then this is the key portion that I was mentioning earlier. So you create a receive port. So you create a receive port, you instantiate a receive port. Then you hook up a callback to the listen method of the receive port. So now you're ready to start listening for messages. But who's going to send you the message? You need to send the native port to whoever you wanted to send you information. In this case, we're going to grab the native port of the corresponding send port of the receive port and give it to C++. So we send that port down to C++, and now we're ready to send messages up to Dart. So now let's go back to C++. And now from here, remember like I mentioned, and notice the line right there, I am importing the Dart API DL, that header for the dynamic library of the Dart API. And this method is actually provided by Dart. This is what you need to call first before you want to engage into, let's say, sending messages back and forth between Dart and your native libraries. So you have to call the method called Dart initialize API DL. This is where it returns that value, and then you check whether it has been properly initialized. You import the Dart API DL, and then you call Dart initialize API. This is the method that I told you earlier that you send the port into, like the native port. This is actually the native port right here. And then you just capture it within your, let's say, within your code. Then after that, in Dart, now you start making those calls. So let's say you do module, lookup function, you find the name of the function, you find it by name, and then this is the native version, and this is the native version, and this is the Dart version. Remember, because this is what establishes the binding. Then after that, all you need to do is just say, send information, and then that's it. In C++, all you need to do is just capture the message right here. You capture the message. And if you want to send information from C++, from your native code, up to Dart, this is how it's done. You create a struct called Dart C object. The Dart C object struct is like the representation of the information that you're going to send to Dart, but in C. Then the Dart C object has a type called, it has many types. This is again part of the Dart FFI, the Dart API. So you do like K-string, K-double, K-typed for like byte arrays. You set up the data, you say I'm gonna send the value as a string. You set up your string, and then you call the method Dart post C object. You specify the port, the native port, and the information that you want to send up. And simple as that, you get the information right on Dart. You can just parse it, you can do anything you want, but in this case now, because you were listening to it, you were able to capture the information. So again, this is more on, let's say, how you want to send data from C++ to Dart. Let's say you don't just want to send like little pieces of information, like primitive data types. You want to send, for example, something more complex. You can actually send a JSON. So you can assemble a JSON in C++. You have more values in there. You can pack up a lot of data. You send it in the same way. You can just parse it as a JSON, create it, let's say you can stringify it, send it as a JSON string, and then you just send it back up to Dart. And then once you're in Dart, you can just parse it normally. This is me, for example, trying to send an image. Let's say you want to send an image from C++ to Dart. This is the way that you do it. You set it up as a K-typed data using, of course, the Dart C object, again, that same type. You specify all of that, and then when you are in Dart, all you do is just decode that value. If it's a JSON, like I mentioned here, if it's a JSON, you can just decode it, and you're good to go. And if it's an image, you can just convert it to an image right away, and you can just consume the unsigned list of 8-bit values in there, and then you should be good to go. Awesome. This is, for example, for in the case where I was mentioning that if you want to execute like heavy computations in the native side, remember, if you send something to let's say, from Dart to C++, it's not like a 1 + 1 = 2, and then you're going to get something back. It's usually something more complex than that. It's either like, let's say you want to execute some machine learning operations, whether you want to do some image processing like the way we do, like we send all those ultrasound images down to our low-level libraries, and we want to process those images. That's not a trivial operation. The way that we do it is we spin up threads in the C++ side of things. But remember that these are not the same as Dart isolates. C++ threads and Dart isolates operate on different spaces. So a C++ code does not know about the Dart isolate. So you make sure that you clean up your memory correctly, you do the allocation and deallocation appropriately. But this is the way that, for example, you want to delegate a heavier computation from the C++ side. You can just spin up a C thread, you perform that right there. And then let's say when your operation completes, then you can send it right up to Dart using the same operation that you've done before, using the Dart post C object. So let's say after your computation finishes, you've prepared, let's say, your response. You just call it, use the same constructs from Dart, and just send the message right up to Dart. Awesome. Okay, so and that's just a way to clean it up. Now the next approach is async callbacks. Async callbacks, again, remember, Dart FFI doesn't support asynchronous functions, and because they're synchronous in nature, it doesn't support asynchronous functions. But there's a way to do async callbacks with that. So it's the same approach. But in this case, async callbacks work by telling the Dart side of things to yield its execution thread to C, so that it can perform the callbacks on its behalf. This may not be the scenario that you want. Let's say if the callback has a long-running operation, which could result like in blocking your UI, and you don't want that, again, especially like in a medical application. So you can use this, but use it with caution. So it's the same way. The thing here, you have to send the pointer of the function from Dart, send it to C, and C can execute it on your behalf. But you can also still send information back up. So it's pretty much the same thing. You still need to, you use the pointer dot from function method, which creates a pointer of your Dart function in a way that you can send it to C++, and then you can execute it on the native side of things. This is the same way, but this is, for example, like the pointer from Dart that you send it back up as a kint64. So it's like an int64 64-bit integer that you can just send it back up to Dart. And then in Dart, you could just execute it. Here is again the same way. You listen for the incoming messages from C++. And then once you've captured the callback and you convert it back to a Dart pointer using, again, the same capabilities provided by Dart FFI, you can then use that callback and call it as any regular method in Dart. Now, the last one, which is the one that is the most recommended approach and is the most modern approach, as part of the improvements to native interop in version 3.1 in Dart, Dart added the native callable, which is a specialized class within the Dart FFI that facilitates seamless communication between Dart and native code. Can anybody tell me what's missing in here? If you have noticed what I've been doing in the other slides, adding something specific for communicating between isolates or communicating between Dart and C++. Can anybody notice? It's missing ports, correct. So that is what it is. Native callables actually use receive ports and send ports, but it does it underneath the hood. So it cleans up, it makes it more seamless. All you need to do, if you want to get your function called, you pass the, let's say, you pass your function pointer, and C++ can call it for you, but it already creates the receive port, it creates the send port, it sends the native port, it sends it right back. It does all of that orchestration for you, but it keeps it a lot cleaner. And if you see here, we have two ways in which you can pass what they call native callables, or like function pointers from Dart. You use isolate local or listener. Isolate local is actually introduced in Dart since 3.2, and it's a convenient way to create a C function pointer from a Dart function, and then you can just call it. And then listener, the other one, listener, actually creates the receive port and the send port and all of that for you. Don't use pointer.from function anymore, because pointer.from function requires either a static method, a top-level function, and it has to be within the same thread. As opposed to listener, you can use any callback, you can use any like a lambda function or any method at all, and you can make it as a callable as long as it is void. You can take any function, it can take any parameters, but it has to be void. And then it's pretty much, like I mentioned, I was just explaining exactly all of that. And this is how a native callable works. So the same thing, you have your pairs. Remember, you have the pair of the Dart signature function, you have the FFI signature, you do your lookups just as before, but you see here that I'm not creating the receive port and I'm not creating the send port. Now you just add the callable listener right there, and if you see here, this is just any regular function, any regular like a lambda function, like a lambda callback, and I'm just ready to listen for incoming messages in here. Then all I do is after, let's say, receive my messages, I close the callable, because you want to clean up resources after yourself, and then all you do is just make the call to the function, you pass whatever it needs, and you pass the pointer to this function right here. So this right here gets passed in here, along, let's say, with any additional information, but you don't need to do like receive ports and send ports and all of that. So it makes it a lot cleaner, and this is just the C++ aspect of that, where, let's say, you can just, within a thread, because remember, you can call it from any other thread, you can just call that callable function, you can pass any information back up to Dart, and you're good to go. And then let's say here in the Dart side of things, you can just receive your information, you can parse it any way you want, you can decode it. Let's say in this case it was like a fake HTTP call, and then you can just grab your information and parse it. But you see, it's a lot more seamless and it's a lot more cleaner, and you don't have to do all that managing of ports back and forth. So some of the considerations, again, in these three approaches, of course, is safety. Unlike the Dart code, errors in native code, such as memory access violations, they can crash your whole application. Proper error handling is also something that you need to take into consideration. Debugging is a nightmare, but at least you're able to, do some proper error handling. Because again, you need to debug, for example, let's say the C++ side of things independently from, let's say, the Dart. But at least once you establish the communication, you can put like proper logs on both sides of the equation, and then you can track, how your things are going. But again, the reason why we did it that way is because our libraries were already properly tested, were properly vetted, and all we need to do is just create the Dart side of things, and we already knew what the API signatures were, what the return and the input parameters were. So at least we knew that we were relying on some valid code. Maintaining it, of course, it makes your code base a lot more complex, and it can potentially increase the maintenance burden. But remember, you're dealing with a lot of better performance when you, instead of doing it on the Dart side of things, you delegate it to something like C++. And platform dependencies, your application, of course, might depend on some of those native libraries, but at least you're bypassing something that I was able to do, bypass like platform channels. There's no platform channels at all. We're talking directly to C++ without involving platform channels, less overhead on that. Something that we're actually doing next is actually leveraging other languages. Remember, I've been just talking about C and C++, but you could do Dart FFI with Go. You can actually do it with Rust, and there are even efforts in the community to implement Dart FFI with Python. Imagine, Python has a vast ecosystem of libraries for data science, for machine learning. So imagine now how FFI can leverage and enable seamless integration with these libraries, allowing Dart applications to actually tap into a larger, vast of ecosystems of libraries out there. So some of the takeaways, of course, are you use FFI Gen to auto-generate your bindings from C headers. Remember, if you have some legacy, let's say, implementations like we do, if you have C++ headers, you're going to have to create that thin layer of like C headers so that you can establish the communication. Defer CPU extensive operations to low-level layers, such as C, C++, or Go, Rust, or whatever. You ensure asynchronous communication between Dart and native code. Try not to always free up the UI thread, and you also try to do it asynchronously. Perform fire and forget calls so that you don't hold like the UI thread. Like I mentioned, keep the main thread free to what it does best, which is painting pixels on the screen. Use native callables for simplified and seamless communication between Dart and C++ code, because then that you alleviate some of the overhead of having to create receive ports, send ports, and all of that. So native callables is the way to go. I'm going to give you some resources. That QR code is actually for these slides right now. So if you want to have those slides right away, just please scan that QR code. Let me know if anybody has access, able to see the slides, let's say, from your devices. So if you scan that QR code, you should be able to have access to all those slides. Perfect. So I'm going to give you a lot more resources. C++ in interoperability in Flutter, how you could do it with Rust, how you do it with Go. Some of these repos are actually from the Flutter team themselves. Like Slava has been actually contributing to some of these. Native callable, which is again the way to go now as far as like creating that seamless communication between Dart and C++. Asynchronous messaging, a lot of examples. And of course, I mentioned at the last, the actual public press release from the Bill and Melinda Gates Foundation and Philips when they announced this application in Kenya and India, which actually with a lot of great success. So any questions? I know that we may be right out of time, but if anybody has any questions, either you can grab me now. If you have a question now, maybe we could take one. Or no, we're good. Perfect. You can catch me outside. But I just want to say thank you so much, everybody. Keep enjoying the rest of this conference, and thank you very much for coming to Fluttercon USA. Thank you so much.